start out today with Unit 4, Lesson 5, kind of Part B, just the reinforcement of the 3 examples we did yesterday. The first problem that I have for you is an example where you have an exponential base on each side. So we've got 2 exponential bases. We have 8 and we have 2. Now, in the last example in your notes, the bases could not be converted into a common form. However, notice the heading at the top says look for shortcuts. What can we convert 8 into that relates to 2? 2 to the third. So we've already laid the groundwork for this in previous examples when we were thinking them out. I'm going to take this 8 and I'm going to replace it with 2 to the third. Now, what do I still have in my exponent though? I still have that 2x and I still have x squared minus 7. Once you convert to common bases, think about the definition of an equation. The left side is the same as the right. If the bases are the same, what else are the same? The exponents. So if I look at my exponents, I could say, you know what? 6x is equal to x squared minus 7. Now we throw out the window all of our thoughts about exponential equations because what type of equation did I just generate to solve? Quadratic. How do we solve quadratics? Put everything on one side and attempt to factor. So x squared minus 6x minus 7 is equal to 0. Does it in fact factor? X, negative 7 plus 1 equals 0. X is equal to 7 and negative 1. Questions on that? All right, so anytime we're dealing with exponential equations and we have 2 bases, look to see if you can convert them to a common base. That will save you a lot of time and a lot of little algebra stuff so it doesn't look like how we did number 3. All right, 2 you-try examples. Let's start with example 5. There were 3 types of exponentials that we spoke about yesterday. The first was if there's 1 base, if you have 2 bases, but you have 3 terms, which is the factoring. I think you can see this is an example of that, example 6. And the other was that if there was a base on one side and a base on the other. Example 5 is how many bases? Example 5 is how many exponential bases? 1. E to the 2x. Now, I understand why you're answering some of you the way that you did. When we were doing the expanding and condensing, we were saying how many bases are here, and then we would expand or condense, correct? When I'm talking about exponential bases and we're referencing equation solving, I want to know how many bases can we isolate or get by themselves. So if I were looking over here, I would have 2 exponential bases, e to the 2x and e to the x, which is how many of the bases have the unknown in the variable. So in this case, I only have 1, so I'm going to isolate that term, which gives me 4 e to the 2x is equal to 5, e to the 2x is equal to 5/4. Please don't convert to decimals. Questions on that? Now, what is our next step when we have 1 exponential base? Convert, right? We want to convert. So we talked about the fact this is kind of like, this is my base down here. This is my power circle. Yes? So it's log base E of what? 5/4 is equal to 2x. Notice now I got the x out of the exponent. What do we know log base E as? ln. So technically, this is really ln of 5/4. Last step, divide by 2. So in your calculator, you would put in the natural log of 5/4, hit enter, and then divide by 2. What do we get for x? What was that? 0.11. Any other answers? ln 5 divided by 4 parenthesis closed, and then divide by 2. 0.11. Questions, concerns, anything? All right, example 6. We already referenced this. This is going to be 2 bases with a constant. This looks like a quadratic form. We're going to solve it in a quadratic strategy. This is e to the x, e to the x. What are the numbers that finish that? Minus 5 minus 2. So I get e to the x is equal to 5. E to the x is equal to 2. How do I solve this? Convert log base e, which is what? Log base e. ln of 5 is equal to x, and ln of 2 is equal to x. Those would be my 2 solutions. You could convert them to decimals. It's up to you. Yes, sir. How'd I factor it? Yep, I did factor it. Questions? Flip the page. Flip the page. All right, if you go online, I'm going to have this as the lesson part B, one video, and then I'm going to edit it, and this will be the start of the new video. All right, so lesson 6 in unit 4 is going to be on solving logarithmic equations. Notice, no longer exponential, we're going to logarithmic. Take a look at all the problems on that page. What do you notice? There's 4. What's in every single one of them? There is a what written there? Starts with an L, ends with a G. There's a log. There's either regular log, natural log, or log with a different base written. You see that? That's what makes, by definition, a logarithmic equation. Exponentials have the unknown in the exponent with no logs written down. Problems like ours now have log or ln. All right, so here are the 3 steps we're going to look for here. We're going to try to isolate the log. Sometimes this means use the properties to take many logs and condense them into one. Rewrite in exponential form, so we're going to use that conversion factor in the opposite direction. Your circles, squares, and hearts. And then we're going to solve for the variable. All right, while you're copying, let's take a little walk down memory lane, shall we? How do we solve a linear equation? For example, if I have 2x minus 1 equals 6, what do you look to do to solve for x? What do you do? Add the 1, divide by 2. So the process is to isolate x, right, in a linear equation. Okay, so now if I have x squared minus 6x equals 0, what type of equation is the second? Quadratic, correct? How do we solve quadratics typically? How do you solve a quadratic? Put everything on one side, equal to 0, and then look to factor. If you can't factor, you go to quadratic formula. If it's a special case like x squared is equal to 9, what method can you use? Square square root method to solve. Yes? Everybody's with me? So those are your three main methods to solve quadratics. Okay? What about when we solve square roots? Have we done square root equations like x minus 1 is equal to 10 plus 5? What do you do to solve for the square root? First you have to subtract 5, isolate the square root or cube root, whatever it is, and then do the opposite operation. Correct? Alright, so what if I gave you one like 5e to the 2x equals 10? What would you do first in the exponential equation? Isolate the base to the power. So as we go through our strategies, we're starting to see more and more instances of isolating the root, or in this case, isolating the base to the power because it's exponential. What we have up here, isolating the log, is going to be our first step in solving this equation. So the log is only this piece right here, ln of x. ln of x has a coefficient, has a bunch of numbers on the same side. So think of ln x almost like a linear equation. You want to get that part of the equation by itself. How do I do that? Subtract 8, so I get negative 2 ln x is equal to negative 3. Divide by negative 2. ln of x is equal to 3 halves. Please don't convert to decimals. According to our list of steps, once we've isolated the log, we then convert it into exponential form. What's the base of ln? E. So I'm going to see e to the what power? Equals x. Do I have x by itself? None. What is e to the 3 halves? Anybody have that? 1.481 approximately because I rounded. All right, let's look at the next example. As we're working through, you're going to need a calculator for the fourth one, so if you want to pull that out, you can do that. That way we don't have a big shuffle there at the end. Example 2, how many logs do I have? 2. Right? Do they have the same base? Yes, because they have the same base, we can put them together by condensing them. So this is why we had to work on condensing in the previous lessons. Condense. Okay, step number 1, bring in the 5. So now I have log base 8 of x to the 5th minus log base 8 of 2. What operation do I ultimately have if I have subtracting of logs? Division. So this is going to be converted down into 1 log of x to the 5th over 2 is equal to 5. Can you see the circle, square, heart form? Now, does it pop out to you? Yes? You see the base, you see the answer, you see the exponent by location. What's my base? To what power? Equals x to the 5th over 2. How do I solve to get x by itself? Multiply by what? 2. Multiply by 2. This is not 16. 8 to the 5th is a very large number that we will end up multiplying by 2. And then, how do I get x by itself if it's to an exponent of 5? What's the opposite of fifthing something? Close, not square root, but 5th root. Okay. So now, this is going to tie into another concept we talked about earlier. In your calculator, you can put in 2 times 8 to the 5th raised to the what exponent? The 1/5. You want to calculate the exact value, that's how you would do that. I would write that down, make sure you know how to put it in, that you know how to convert. Not all of your calculators allow you to change the index. It'll have a programmed square root and cube root, but maybe not a higher root. What do I get approximately for x? What'd you get? 9.18. Anybody else get something different? 9.18. Put it in your calculator. Let's go. 9.19. We got 9.19 rounded. Yeah. 9.189, which is 9.19. Okay. Yes, sir. PEMDAS, what comes first? Not multiplication. Good question. All right, example 2. Good? Yeah. What is that as an exponent? So I wanted to calculate all of this to the 5th root of that. No, because the 2 isn't to the 5th power.
Oh, okay.
Right?
Yeah.
Like if you were thinking about doing it by hand, you'd want what was under the root, that big number, then you would take the 5th root of that. So it's basically like I'm offsetting what's underneath the root in parentheses. So I take the 5th root of all of that. Yes, sir.
How do you, from the log to just without the log, what does the log go?
Which 5? This 5?
Yeah.
It went. Hold on. This box got converted into this box here.
Okay.
You're good? And then I did more work to multiply both sides by 2 and keep going. But this became that, and then I went here and all the way down. Good? All right, example 3. Don't panic. Breathe. It's going to be okay. How many logs? How many logs? Take a look. 3. Okay? The strategy when you have 3, when you have logs on both sides, is that you have to first take the left side, just like we did in the last example, and we need to condense. Okay? Notice I didn't bring any logs to the left. I kept everything on the right, and I'm going to condense the left. What operation do I use when I'm adding 2 logs? Log base 2 of x times x plus 2. Everybody knows this is all in the answer spot, correct? Log base 2 of x plus 6. Property number 4 says log base 2 is equal to log base 2. Doesn't that just mean my answers are the same? They're the same. Property 4, look back in your notes if you forget. I believe there was an x and a y here, and then we just said x equals y. So once we get to the point that we have a log equal to a log, we can apply property 4, which says the answers are equal. So here is my question. What type of equation do I have? Quadratic. How do we solve a quadratic? And I'm not making fun of people from the South. On purpose. Bring everything to one side. X squared plus x minus 6 equals 0. Factor. X minus 3 plus 2. Is that right? Everybody's nodding yes, that's right? Look at it. Is it right? I need a positive 1. The outer and inners add to positive 1. No, it's plus 3 minus 2. Oh. Everybody got 1.1? Nobody even put it in the calculator. Is that how you factor? No. Alright, so now I'm going to blow your mind. Are you ready? The answer to this starts as this, and then the answer is just 2. Why? Why? Jordan?
You can't have a negative in your log.
If I take -3 and plug it in right here, can that ever happen? Log base 2 of -3? No. So guess what? You have to check your solutions. We started checking solutions when we started doing square root equations, if you remember. Right? Because you can't have a negative under the root. Now we have a domain consideration. You can't have an answer that does what? Gives you a negative in the root. You can't give me an answer that violates the denominator of a rational. All of the rules that we are learning, those 3 domain rules, play into the solutions that you give me that x are allowed to be. Questions? So the only answer I have is +2. I'm going to ask one more time before we shut this down here with doing problems by hand. Is there anyone that has a question why I had to eliminate -3? What happens on a test if you don't check your solutions? You're going to lose points because you're not following all of the steps and you're telling me things that absolutely cannot be answers. All right, solve using the graphing calculator. Pull out your calculator. All right, so let's review something. Does this look familiar? What I wrote in blue? Here's an equation. Set y1 to the left, set y2 to the right, and solve. What would I be solving for in the calculator? I'm graphing y1, I'm graphing y2. Where would the solutions be? The intersections, correct? Intersections. Correct? And whatever I get for the x values, because my equation only has x's in it, that's what I would be solving for. You need to know that. That is on your final exam. We've done a little bit of it in every single unit of using your calculator to solve equations. So this is no different. The only difference is now what I feed into y1 and y2 may include an exponent or it may include a log. So following the same structure, what would I put in for y1? y1 is what? Pattern. Develop the pattern. What's y1? ln x. Natural log of x. What's y2? 4 minus x. Ooh, a line. Crazy. Okay, put it in. How many intersections do you see in the graph? 1 or 2? 1. Find out what it is. We go to second trace. Calculate 1.9. No? What do we get? 2.9. Okay, I'm going to keep going until the class tells me what the right answer is. 1.9, 2.9, 7.9, what is it? 2.9. Do we care what the y value is? No. 2.9 is what's generated when we go through all of the steps. Am I just using trace to estimate the intersection? No. I am calculating the exact intersection point. Second, trace, the calculate menu, choose intersection. Got it?